Hi ladies and gentlemen, in this video I will tell you about cascading of multiplexers. So in this we will see how two 4 is to 1 muxes are cascaded to form an 8 is to 1 mux, and how two 8 is to 1 muxes are cascaded to form an 16 is to 1 multiplexer. So let me start with that presentation. So the speech is organized into your learning outcomes cascade of two 4 is to 1 muxes, cascade of two 4 is to 1 muxes using Verilog, and 16 is to 1 mux by cascading to 8 is to 1 multiplexers, and summary of your understanding. So what you will learn in this session is that you will learn to cascade to 4 is to 1 muxes to form an 8 is to 1 mux. Then you will implement it in QUCS and Verilog. Then you will learn to cascade two 8 is to 1 muxes to form a 16 is to 1 mux and implement it in QUCS and Verilog. So cascade of two 4 is to 1 muxes, you can take two 4 is to 1 muxes and they can be cascaded as shown in this figure. See, this is the first 4 is to 1 mux. Here in the left side there is one 4 is to 1 mux. On the right side there is another 4 is to 1 mux. And the first two both have four inputs and two select lines S1 and S0, which are connected together, S1 and S0. Then there is an enable pin here. Here it is a logic low. Enable is a logic low, so that when S2 equal to 0, this left chip is enabled, and when S2 equal to 1, the right chip, because after inversion this enable is low, and the right multiplexer is activated. So the outputs are here. These are the two outputs of the muxes. They are ORed together to form the final output Y. So this altogether this works as an 8 is to 1 multiplexer. So the first four inputs I0, I1, I2, I3 are given to the left 4 is to 1 mux, and the remaining outputs I4, I5, I6, I7 they are given to the right 4 is to 1 mux. So that these select lines are S1 and S0, and S2 is given to the enable pin, so that when S2, S1, S0 counts from 0, when 0, 0, 0 to 0, 1, 1, 1 for the first four counts, that is 0, 0, 0, 0, 0, 1, 0, 1, 0 and 0, 1, 1. That is when S2 equal to 0, this chip is enabled, and for these counts 0, 0, 0, I0 will come out. When I0 comes here, this input, this output input to the other input to the OR gate is a 0, so Y is I0 or 0, that's a I0. When it is 0, 0, 1, I1 comes out. When it is 0, 1, 1, I2 comes out. 0, 1, 1, I3 comes out. When it is 0, 1, 0, I2 comes out. And for the counts from 1, 0, 0 to 1, 1, 1, that is when S2 equal to 1, this chip is disabled and its output is 0. And this chip is, the right chip is enabled. So that for the count 1, 0, 0, what will happen is this chip is enabled, and the first input, the 0th input 1, 0, 0, that is I4 comes out. When it counts 1, 0, 1, when S2, S1, S0 is 1, 0, 1, I5 will come out. And when S3, S2, when S2, S1, S0 is 1, 1, 0, I6 will come, and when it is 1, 1, 1, I7 will come out. So it is by making use of this enable pin that I cascade to 4 is to 1 muxes. Now this QUCS diagram shows two 4:1 muxes cascaded to phoneme and 8:1 mux. Here as said earlier, this enable pin, this is connected to the MSB, that is a 4 nanosecond, 4 nanosecond. This is a MSB bit, and it is inverted and given to the enable of the other gate. Here these are my S2, S1 and S0. These are 2 nanosecond, 2 nanosecond, and this one, this is a LSB that switches states in every 1 nanosecond. Now these inputs, the first inputs I0, I1, I2, I3 alternate are given, like it's a 0, 1, 0, 1. Here the pattern 0, 1, 0, 1 is given here. Here also the pattern 0, 1, 0, 1. So that I0, I1, I2, I3 is a 0, 1, 0, 1, and I4, I5, I6, I7 is 0, 1, 0, 1. Alternate zeros and ones are given as the data. Now here we can see that the enable is complemented, and S2, S1 and S0, they are shorted together for these things. The outputs are connected to OR gate, and final output is my OP. Now we can run this simulation and check this truth table. So here I have given 0, 1, 0, 1. So here it is coming in the other way, because this S2, S1, S0 are active low input. So here if you say 0, 0, 0, it's a 1, 0, 1, 0, 1, 0 alternate. When it is 0, 0, 0, first comes I0, I1, I2, I3, I4, etc. Or else, better still, I can connect these things to inverters. That will also work. So this is how I cascade to 4:1 multiplexers to form an 8:1 multiplexer. Now how do I make a Verilog code for this? I can use a Verilog to cascade to 4:1 muxes to form an 8:1 mux. I will show you that code here. Yeah, this is a cascaded mux 4, and here I can I include the 4:1 multiplexer I made earlier. So I need a 4:1 multiplexer block for this. So here I include a 4:1 mux. This I made in the previous classes. Then I start with a module some cascaded mux for 2 muxes are cascaded, and the output is a wire, that is Y, and the input wires are I0, I1, I2, I3, I4, I5, I6, I7. Then 3 select lines are there, S0, S1, S2. They are all wires. Now there are some internal nets, like I need to complement this S2. So there is a complement of S2, that is a wire, and AB. These are the outputs of the 2 4:1 muxes. So for that I generate 3 local nets. Okay, I declare 2 local nets. Then what I do is I have to complement this S2. This goes to my enable. So for that I use a NOT gate. S2 comp is equal to S2 complement, the complement of S2. That is what it does. Then earlier when I made this 4:1 multiplexer, I made it with active high enable. Okay, so for that one I take 2 instances of the 4:1 mux. Let this be N2, that is output is a and inputs are I0, I1, I2, I3, because these are the things that go to the first multiplexer, and S0, S1 and S2 complement. This should be low. This should be high. Comp should be high, because when S2 equal to 0, this mux should be activated. For that, this should be a high. So for that I use this complemented S2. So output of this 4:1 mux is A, and I make another instance of the 4:1 mux, say N3, that is output is B. And what are the inputs to this? This should be I4, I5, I6, I7. What are the select lines? S0, S1, S2. Why S2? Because when S2 equal to 1, this mux is activated. That is for the counts from 100 to 111. Then what I have to do is I have to OR these two outputs A and B, so that what is that output? That should be the output of this multiplexer Y, or Y N4 Y comma AB. So A or B becomes Y. So this is how I make this. Now I have to run this code. Open a terminal here. Now this runs without any error. Now I look into a test bench wherein I will include this cascade on Mux4 and apply some signals and test it. So here you can, what in the first line I include this cascade on Mux4, this device under test, then some module test bench registers. These are the inputs like I0, I1, I2, I3, I4, I5 to I7. S0, S1, S2, these are held as registers, and output is a wire. Now I make an instance of this cascaded Mux4 with the cascaded Mux4 is Y is I0 to I7 and S0 S1 S2. Then I give these signals. I give random patterns here, and I test this. Now I will run this code. I will run this test bench. Now this also compiled without any error. So this is a dot out. Now you can see that this is how it behaves. Now when we say this has to behave like an 8:1 multiplexer. So when S2, S1, S0, this is 0, 0, 0, I0 should come out. So what is I0? This is a 1, so output is a 1, it is I0. Now when it is 0, 0, 1, I1 should come out. I1 is S0, so Y is S0. And when it is 0, 1, 0, I have to count this way, 0, 1, 0, I2 should come out. I2 is a 1, so output is Y is a 1. S2, S1, S0 is 0, 1, 1, so I3 should come out. It's a 0 that comes here. And it is 0, 1, 1. 0, 1, 1 is a 3, so I3 is a 1, so Y is a 1. Now when it is 1, 0, 0, that is I4 should come out. I4 is a 1, so Y is a 1. Now it is 1, 0, 1. 1, 0, 1 is a 5, so I5 should come out. I5 is a 1 here, so Y is a 1. Likewise, this is 1, 1, 0. 1, 1, 0 is I6 should come out. I6 is a 1, so Y is a 1. When it is 1, 1, 1, when S2, S1, S0 is 1, 1, 1, I7 should come out. I7 is a 1, so it comes out. When it is 1, 1, 1 and I7 equal to 0, Y becomes a 0. So this is how I cascade to 4:1 muxes to form an 8:1 mux. This is the implementation in QUCS. This is the implementation in Verilog. Now, how do we cascade to 8:1 muxes? Very similar to this. So only thing is I have two 8:1 multiplexers are cascaded to form a 16:1 mux. So this is how we do. Very similar to that. Only thing is here there are two 8:1 mux. Each has 8 inputs and 3 select lines. 3 select lines are sorted together. These are inputs from I0 to I7. These are I8 to I15. So here it's assumed a logic low enable. So this is when A is 0, this mux is enabled. When A is 1, this mux is enabled. So these are ORed. Okay. So when this A, B, C, D, they counts from 0, 0, 0 to 0, 0, 0, 0 to 0, 1, 1, 1. That is for the first 8 clock cycles. What will happen? These are I0, I1, I2 to I7, they come out. For the next 8 clock cycles, that is from 1, 0, 0, 0 to 1, 1, 1, 1, I8, I9, I10, etc. to I15 comes out. Okay. So this you can see the simulation in QUCS. Here this is a cascaded form of that. This is an 8:1 multiplexer from the QUCS component list. So these are connected like this. You can see that this select lines are complemented. They are active low, so they are complemented. Now this is my enable pin. When enable equal to 0, this is enabled, and when it is 1, the right side mux is enabled. So if I run the simulation, here these inputs are connected like I think a strange pattern is there, 1 1 0 1 0 0 etc. We will see that how that behaves. Now you have this thing where these enable S2 S1 S0, they count from 0 0 0 to 1 1 1. So how these come, this is a final output. So this I have to get I0 I1 etc. So this pattern here is 1 1 0 1. Okay, so the pattern coming here is 1 1 0 1, then 2 zeros 1 1. You can see that there are 2 zeros, then 1 1. Okay, 2 zeros 1 1 1. I have 2 zeros 1. Then you can see that these are ones, like this is a 1 1 0 1. What comes here is a 1 1 0 1. Okay, then there are 0 zeros. Here if you see, these are 2 0 zeros. Okay, 0 zeros. Then I have a 1 1. Then I have a 1 1. So that makes all clock cycles from 0 0 0 to 1 1 1 1. You may make such a circuit at home in QUCS, and you can appreciate this. So let me go back to my presentation. What you understood is you learn to cascade to 4:1 muxes to form an 8:1 mux. So what you utilize is the enable pin. So during half the clock cycles, one mux is enabled, and during the remaining clock cycles, the other mux is enabled. So the outputs are rolled together. Then we implemented it in QUCS and Verilog. Then you learn to cascade to 8:1 muxes to form a 16:1 mux, and you implemented it in QUCS. And that is the end of this presentation. I thank you all.